Hi everyone, welcome back. Today we're going to break down another really common system design interview question. This time it's going to be design Dropbox. This is also referred to as design Google Drive sometimes. They're largely the same question. It's a super popular question. It's asked at all of the top FANGs, really popular at Google and Amazon, shows up a ton at Meta as well. So by way of introduction, just quickly, my name's Evan. I'm a former interviewer and staff engineer at Meta, and I'm the current co-founder of Hello Interview. And Hello Interview is a company that helps candidates prepare for their upcoming interviews at FANG companies. And this is largely via mock interviews with current FANG interviewers. So between asking this question at Meta and asking it at Hello Interview, I've probably asked it, I don't know, maybe around 50 times. And I have a really good understanding of where candidates do well and where they trip up. And this is candidates of all levels. So we're going to walk through this as if it's a real interview, but of course I'm going to be periodically teaching, jumping in with tips, sharing the perspective from an interviewer. This question is a little bit on the easier side. So it's asked most frequently of mid-level candidates. This is E4 or L4 candidates, but it also shows up a ton for senior and even staff candidates. So useful for all levels, and I'll call out the deltas as I mentioned, as it pertains to leveling as we go. Lastly, if videos aren't your thing, you don't want to sit here and listen to me for an hour, you can head over to hellointerview.com where I have a detailed write-up. Sorry, I was on the wrong page there. I have a detailed write-up of this very question. So you can come over, read through this instead. This will be linked in the comments below. And then that page that you just saw there is that you can come here if you want to suggest whatever you want us to break down next. And I'll continue to try to make videos for each of these that we break down. So come over here, propose a new system design interview question, and vote for the one that you want to see next. We'll break it down, every 2 weeks or so, we'll do a new one. Awesome. Okay, well, without further ado, let's get into it. All right, before we dive in, let's take a moment to talk about the approach to the problem. This is the roadmap that we're going to follow here today, and it's the roadmap that I suggest that you follow for any of your system design interviews for which you're designing a user-facing product, like Dropbox is. So we're going to start by defining the requirements. The requirements will consist of functional requirements, which are the core features of our system, as well as non-functional requirements, which are the qualities of our system. And then we're going to move on to defining the core entities that are persisted and exchanged via the APIs, which leads naturally to us defining those user-facing APIs. Before we move on to our high-level design, so this is where we'll draw our boxes and arrows in order to sketch out a high-level design whose primary goal is to satisfy those core functional requirements, those core features of the system. So at this point, it should be relatively simple. And then we're going to move on to our last step, which we call deep dives. And this is where we go deeper in order to expand on our high-level design and make sure that the system is able to scale, fault tolerant, all of those things which we'll see when we define our non-functional requirements. So first up is those functional requirements. Again, these are the core features of the system. So what is the product supposed to do? You want to take this moment to identify those top 3 features. Now, if it's a system that you know well, this should be pretty easy. If it's a system you don't know well, then this is the time where you would ask the interviewer some questions in order to better understand what the requirements of the system may be. Now in our case, for something like Dropbox, they're pretty straightforward. We know that we need to be able to upload a file from remote storage, for example, or to remote storage. Also download a file, in this case, from remote storage. And then we want to be able to automatically sync files across devices. So this is the case where if anyone's used this feature in Dropbox, you set up a local folder on your local machine and your local desktop. And then anytime a file is uploaded to the remote storage, it's automatically synced with your local file system. Likewise, if you were to drag and drop a new file into your local folder, then it should be automatically uploaded to your remote storage and then synced with all of the other connected local devices. So hopefully that makes some sense. We'll talk about, of course, how to implement this. And then one thing worth calling out here is that this system is not going to require us to design or roll our own blob storage. So that's actually a different system design question that's sometimes asked, design S3 or something similar. So we're going to just say that that's out of scope. So out of scope is, roll own blob storage. Cool. And then next up we have those non-functional requirements. So the non-functional requirements are the qualities of the system. So these are the things that you're used to reading in your books of low latency, fault tolerant, durability. We talk about CAP theorem here, all of those things. But most candidates overlook this. They breeze through it, they write some generic words, and it's entirely uninformative. And so for senior and staff and up candidates in particular, the non-functional requirements are so important because these are what's going to inform or lead your deep dives later on. And your depth is necessary for you being able to be leveled at those higher levels, senior plus. So for example here, the first thing that we can talk about, as we usually will, is CAP theorem. Do we prioritize consistency or availability in the context of CAP theorem? Of course, partition tolerance for the scale system we're dealing with is a must. So in this case, we're going to prioritize availability over consistency. So availability is more important than consistency in this case. But importantly, we're going to put that in the context of this system. So what does that mean here? It means that it's okay if we upload a file or we change a file somewhere else in the world, say Germany, and somebody in America goes to read that file shortly afterwards, and they still see the old version of the file. That's okay. That's totally fine within our system. And we're willing to take that compromise such that everybody can still download a file when they request, download, view, whatever it may be, when they request to download or view that file respectively. So in our case, availability is much more important than consistency. Some other things that we want to consider in our non-functional requirements is we want to have low latency uploads and downloads respectively, right? So in this case, it's not just low latency, that's the buzzword. It's what in the context of the system, uploads and downloads. And then we'd want to quantify it. So how much time? Now in this case, we don't know because files vary. So I'm kind of going to take a cop out and just say as low as possible. And then the next thing that we want to consider here is that we want to be able to support large files. And this is something I can quantify. I want to say as large as 50 gigabytes. This is actually exactly what Dropbox supports. And then as part of that, we should have resumable uploads. So this is the case that if a user tries to upload a 50 gigabyte file, that can take some time. If their system or they lose their internet, whatever it may be, halfway through that download, we don't want to make them start over. That would suck. We want to allow them to pick right back up where they left off. And then another one that we're going to add in here is that high data integrity is really important. So this basically means our sync accuracy is high. So yes, eventual consistency is fine. It can take a couple seconds, but by the time things have stabilized into a consistent manner, the integrity of our data should be high, meaning what's in one folder should also be in remote storage, should also be in another folder. Hopefully that makes sense. So these are the ones that I identify as particularly important. These are what are going to lead our deep dives. We may come back and add to these as we're going, and this is normal to do in an interview. As you're going, you might think of new ones, come back, keep it updated. That would be great. Now just quickly before we move on to the core entities and the API, I want to call out that you'll notice I didn't do back of the envelope estimations yet, and I actually don't plan to up front here. And this is generally my suggestion. It's good to get an understanding of the scale of the system up front. In this case, we're talking about Dropbox scale, talking about hundreds of millions of daily active users. And as it pertains to storage, we're going to use some nearly infinitely scalable technologies like S3 or other cloud-hosted blob storage technologies. So it doesn't matter too much there. Now, estimations are important. I don't want to kind of belittle them. And you should use them when you're actually within your high-level design. So you should do a high-level estimation when the result of your calculations is going to have a direct impact on your design. That's the general guidance that I give. And typically it's hard to know that up front. And candidates here will just do some daily active users and some total storage and some bandwidth estimations and then go, wow, that's a ton, and then keep moving on with their day. And that's a waste of time. It didn't inform the design. And I didn't learn anything about the candidate other than they can maybe do multiplication or division. So that's my suggestion. As always, over-communicate with your interviewer. If you're going to take that approach, tell them that's the approach that you're going to take. I kind of highly expect that they won't disagree with you, but it's worth communicating that. Anyway, let's move on now to our core entities and API. So core entities here, I know other people will refer to this as data model or data schema. The reason that I say core entities, and I choose this word intentionally, is because oftentimes at this point in the design, we're only 5 minutes in, I don't know all the columns. I don't know my full schema. I'm still trying to figure all of that out. But what I can take a moment to do is just sit down and really think about what core entities or objects are persisted and exchanged within my system. And so in our case, the main one is that we know there's a file. And this is like the raw bytes of the file. We're going to store those in S3 or some other blob storage. And then importantly, we also know that there's file metadata. So this file metadata is going to have things like the file name, the ID, MIME type, size, whatever else, right? And then lastly, and maybe least importantly, in some cases maybe I recommend you don't even put this because it's more of a distraction than anything else, but of course there are user objects within our system. So if you're feeling comfortable at this point to outline all the columns, and in the case of Dropbox, it's pretty simple. The only ones that we would have would be file metadata, having those that I just talked about. You can go ahead and just do it in line now. I opt not to, and I end up documenting the full fields or columns directly next to my database while we're doing the high-level design, so that it's easy for me to keep it up to date. And you guys will see that a little bit later on. But those are the main core entities, really straightforward. Now, as we move on to the API, you'll see everything is growing on each other. So we're going to use those core entities as the kind of inputs and outputs of our API. And we're going to make sure that we have an API endpoint or a handful of API endpoints that satisfy each of our functional requirements. That's the goal here. Do we have a user-facing API that can satisfy each of those functional requirements? So let me make sure that they're in view. So the first one that we're going to have is we need to be able to upload a file. So this is going to be a post files, and maybe the body here is going to be the file and the file metadata. So you can kind of see this nice abstraction where I might not know all of what's in the file metadata yet, but I know that it's going to need to be passed in here. And what does this return? I don't know, the 200. And then what else? We need to be able to download. So we're going to have get files, and this is going to take in a file ID as a path parameter. And what's it going to return? It's going to return the file and the file metadata associated with that file. Cool. So super easy, right? Let's keep moving here. The next one that we have is that we need to be able to automatically sync files across devices. Now that's going to require calling our upload and download endpoints respectively, but we probably also need to know if something changed. Like you can imagine that in these local folders, or at least our local clients, they're going to be calling and asking, hey, what's changed? And once they get a list of what's changed, then they'll be able to upload or download respectively. So I'm going to call this get changes. It's going to take in some timestamp. This is going to be the time that we want changes from. And what's it going to return? Well, this is probably going to return, and this might change as we design, but I'm going to say like it's a list of file IDs. Like these are the ones that have changed. This is what need to be synced. And so we can take those file IDs and then call our download for each of those file IDs in order to update them locally. So a couple things here to call out. One, there's shorthand going on. This is great. A lot of candidates spend too much time in the API. By being able to reference your core entities, you can move quicker. I think that's important. These make sure that they satisfy our 3 functional requirements. In this case, it was a one-to-one mapping. It's not always the case, but it was convenient here. But some astute viewers are going to be pointing out these API endpoints are kind of wrong. And that's actually true. The API endpoints, in order to upload a file, for example, is not going to be a single post files upload like this. But at this point in the interview, most candidates, from my experience and how many times I've asked this, don't know that. And that's okay. So we're going to show how we'll need to come back here and update these later on. As we go through our high-level design and we go through our deep dives, we'll find out that these API endpoints actually need to be a bit more complex. There needs to be a bit more going on. But this is our first guess. And so we're going to run with this first guess and take this into our high-level design, and then we'll come back and we'll amend them as needed. The last thing that I'll say, which I've said in the first 2 videos as well, is I'm careful to not put user explicitly here in the body. Of course, we'll want a user ID on upload, but I usually just mention verbally to an interviewer that the user ID is going to be present in the request via the header, either via a session token or a JWT. So that's where we're going to get the user information. It's minor. Most interviewers probably won't care. Some will. But of course, this is a security concern. It means that anybody could falsify a request here and upload or download a file on behalf of another user. So something minor there. All right, let's move on to the high-level design. All right, now it's time for the fun stuff. So let's start sketching out our high-level design. And as a reminder, the goal of our high-level design is to satisfy these 3 core functional requirements. Now, conveniently, so too did our APIs. Our APIs satisfied those core functional requirements. So actually the natural thing to do here is just go one by one through our APIs. So being clear about what the user input is, and then making sure that our system can satisfy the requirement and return the expected user output. So let's go ahead and do that. I'm going to draw the design over here to the right. I'm going to start with a simple, what is going on here? I don't want any fill. Okay, I'm going to start with a simple client box. I'm going to introduce this is going to be the load balancer and the API gateway. This could be AWS managed API gateway, but this is going to be responsible for handling some of that middleware like authentication, rate limiting, SSL termination, and then importantly routing. So in a microservices architecture, this guy is going to be able to take those API endpoints and route them to the correct service. So we'll collect our client to our API gateway. And now we're focused strictly on this upload files API here. So we're going to introduce some file service, I'm going to call it. And when a user goes to upload a file, let's say this is our post. I'm actually going to do this in shorthand to make it clearer maybe. I'm going to call this upload. So when a user goes to upload a file, it's going to hit our file service. And then at this point, we're going to have 2 things. We're going to have our file and we're going to have our file metadata, all right? And so we need to store both of those. Now we wouldn't store both of those in the same storage technology, in the same database. And the reason for that is they're very different in nature. So oftentimes, when it comes to raw files or the raw bytes of the file, not oftentimes, this is almost every single time, we want to store those in blob storage. Blob storage is optimized for being able to store cheaply these large blobs of bytes, these large blobs of data. So in this case, we're going to use S3. So we're going to call it blob storage. And this could be any that you want. If you want to use GCP, that's fine too. I'm going to use S3 in this case. So the first thing that we're going to do is we're going to upload file. And then once the upload is complete, this is going to return with the link to where we can access that file in S3. So then importantly, we're going to have this file metadata DB. And after the upload is complete, we're going to write to our file metadata. So write metadata. And that metadata is going to look something like this. So we have file metadata. We're going to have a file ID. We're going to have a file name. We're going to have that MIME type. This is like the type of the file. Is it a PDF? Is it an image, etc.? We'll probably have the size in bytes. Of course, we'll have the owner ID. This will be a foreign key to our user table. Potentially shared, though we specified that it wasn't in the scope of our requirements. And then importantly, this is where we'll have that S3 link. This is a link back to where the file is actually stored in blob storage. And then I'm going to do this as shorthand. Of course, we'll probably have some other less important metadata, but this is the main content that we'll want to store. Now, as I mentioned earlier, I'm putting this directly beside my database because as we complete the rest of our API endpoints, we may find that there's other stuff needed here. And this makes it nice and handy. We can just kind of update it inline, which will be great. And so I'm also going to write here, storing the raw bytes of the files. So storing the actual files themselves. Great. So client uploads, go to the file service, upload the file itself to blob storage, save the metadata, and then return with a 200 that the upload was successful, or of course any other error code if there was a failure. So that's the first one, pretty straightforward. Now, the next one is equally as straightforward. This is get file given a file ID, and this is going to go in the same path. So I'm now going to have that get file, and it takes in a file ID, and it's going to hit our file service. It's going to use that file ID to look up the relevant metadata, and then that's going to give it an S3 link. So we'll go get the actual file from S3, and then we can return it to the user. And so what would actually happen here in practice is that we're going to get this file metadata. We'll return that metadata directly, and then we can download from S3. So maybe we'll go like this. We're not going to download to our file service once and then download again to our client. So in this case, it's download directly from S3 using that S3 link that was returned via the metadata. So there's other optimizations that we can make here and we'll actually need to make to this upload download path. And we'll talk about that in our deep dive. But this is the simple version here. So at this point, we can upload files, granted small files, but we can upload files and we can download files. In the case of download, we'll download them directly from S3. So great, super straightforward there. Now let's focus on our last and most interesting functional requirement, the one to automatically sync files across devices. So the first thing that I want to note here is that we oftentimes just put this client box nice and small and abstract out the client for these system design interviews. And that's appropriate most of the time. But for some systems, this one being one, another being those that require streaming and adaptive bit rates like Spotify, Netflix, YouTube, etc., there's actually logic on the client, which is really important. And we want to reflect that. So let me demonstrate that by making this client box a lot bigger so that we can put some things in it, right? Make it meaningful. So this is our client, and the first thing that I want to make sure that I put in it is we're going to have our local file or our local folder, I'll call it. So this is the folder that we're syncing, right? So that's the first thing that's here. And then the other thing that's going to be on here, importantly, is that we're going to require that users download some client application, either on their Mac or on their iPhone or Windows machine or whatever it may be, right? So we have some client app. And this client app is going to be responsible for syncing remote and the local file, the local folder here, right? Okay, that makes a good amount of sense. So let's break this down. What does it take to do this file syncing in the most simple way? So there's two types of syncing directions, maybe we can call them. The first is that remote changed. And in the case where remote changed, we want to make sure that we can pull in those changes. So we can pull for changes periodically maybe, and then we want to download the new file, and replace the old potentially. Excuse the kind of misspellings, I'm just going to run with it anyway. And then the second thing that we want to do is what happens if something happens in the other direction. So if local changed. So if local changed, then we need to upload the changed files to remote, right? So pretty straightforward. Those are the two things that we need to be able to handle here. And so let's talk about how we would do it simply. So let's start with maybe remote changed. So in the case that remote changed, let's do this. I'm going to add a new server. This is going to be our sync service. And so some strong arguments as to whether or not we're over modularizing here by separating these two. I'm going to just kind of look past that for now, especially since this service will grow in complexity during our deep dives. But we're going to have that get changes API here. And so that API is going to look for anything that has changed. Maybe it's going to directly ask the file service to query its file metadata and tell us the IDs of anything that changed. Importantly, that means that we need some additional data here, right? We probably want the creation timestamp, but then we also want the update timestamp, right? And so this way we can just query our file metadata, see which files have been updated. We'll get those to our sync service. Our sync service is going to respond with the IDs that have been updated. And then our client app is going to download. So it's going to ask for the file metadata from each of those IDs, get that metadata, and then download directly from S3, right? So you might have just noticed we had an additional round trip. We had the get changes, and then we did the download. So potentially you want your sync changes to not just return the ID here, but to return the full metadata. So you can go and download directly without that additional call. That seems reasonable to me. This will all still evolve in our deep dive. But if I just noticed that in an interview, I would say that seems reasonable. And I would come here and say that we return the full metadata. So our sync service gets the metadata of any file that changes, and then our client app will download them, put them into our local folder, replacing any ones that already existed there. Okay, easy. The next one, local changed. So in the case that local changed, we want to upload those changed files to remote, right? So if local changed, we're going to notice that. And the big question is, well, how do we notice that? And the answer is that natively, each of these operating systems provide an API in order to watch changes to a folder or directory. So actually, let me write those down. In the case of Windows, they offer something that's called File System Watcher. So you can look this up on your own time. This is just an API that's exposed via the operating system, which is constantly watching any changes to a local directory. And then based on changes to those directory, you can, of course, do something. And then in the case of Mac, what is it? In the case of Mac OS API, it is called FS Events. So there's an object exposed called FS Events, which has itself a handful of endpoints, such as watching from a local folder. So in our client app, we'll have some code depending on which client and operating system the client's downloaded on. In order to see changes, when a change occurs, we will then upload them via our normal upload path. And we'll just need to make sure that we make any updates here. So maybe we re-upload to S3, change the S3 link, and then update the update time. Right? That's a real simple way to handle this. Now, one question you may be asking is, how do we know, for example, that when remote changed and we pull for changes, how do we know that we don't already have that file in our local folder, in our local file system? And that's a great question. And the truth is that our client app is actually going to have something else here. And so maybe I'm actually going to represent this visually. We are going to need to have some, I'm going to call this a local DB. So we're going to have some local database, which has the metadata, including the IDs and some of the additional information about each of the files that are in the local file system. So when a new file is updated, we can look in that local DB in order to determine whether or not we've already downloaded that file ID. And if we have downloaded that file ID, then we'll have kind of a reference from that file ID to wherever it is in our local folder. So there's going to be some important stuff that we'll talk here about what's called fingerprinting in order to hash and identify a file as well. I'm going to save that a bit for the deep dives, but this is kind of the simple way that we would do that. We had some additional local database. We're able to look here and cross-reference the metadata that's stored here with any of the metadata that's stored in remote. And we'll want to make sure that those two things remain as consistent as possible. All right, so our high-level design is in place. And as a reminder, if we look back at our roadmap, the high-level design was simple but did a good job to make sure that it met all of our functional requirements. Now, our last step in the process is to lead some deep dives. And this deep dive's goal is to make sure that we satisfy our non-functional requirements. And so how deep you go here and how proactive you are in leading is largely a function of your seniority. For example, if you were a mid-level candidate, then what you have here is pretty good. This is close to getting hired, to be honest. But the interviewer may jump in now and ask you some questions, lead you in the right direction, some follow-up questions, and hope that you have competent answers to. Now, if you're a senior engineer or, of course, a staff engineer, then you'd want to continue driving the conversation at this point. You'd want to come over here to your non-functional requirements, as we'll do here in a second, go one by one through them, and make sure that you can enhance your design in order to ensure that they're satisfied and kind of go deep in each of the respective areas. So for senior candidates, you want to go deep in maybe 1 to 2 places. For staff candidates, you want to go deep in 2 to 3 places. And of course, the level of depth should be increased. You should have more hands-on experience the more senior you are. And as a result, you should be able to go deeper on each of these components. So let's do this now. I'm going to go deep in maybe more areas than is necessary in an actual interview. But this is illustrative. It's more so to teach as opposed to adhering to exactly what you would do in a session. So let's come over here. I'm actually going to go out of order. I'm going to start with supporting large files as large as 50 gigabytes and resumable uploads. And you'll see why I do this in a second. It actually will have consequences on some of our other non-functional requirements. So let's come over back to our design and talk about why this wouldn't work. And actually, I would point this out to a mid-level candidate as an interviewer. I would say this design's great, but it actually won't work for large files. This design would only work for files as large as 5 to 10 megabytes. And there's a reason for that. So there's 2 issues that we currently have when we want to upload large files. Let me maybe start tracking here. So upload large files. And I'm going to say 50 gigabytes. So the very first issue that we have is that this upload path is actually redundant. So we upload the file once to the file service, and then we upload it a second time to blob storage. This is a waste of bandwidth, it's a waste of CPU resources here on the server, so it's entirely redundant and unnecessary. It's kind of issue 1. And then issue 2 is that we couldn't even upload this through this path if we wanted to. And the reason for that is that request bodies have a limit. This limit is oftentimes set by browsers, it's set by servers, it's set by the API gateways respectively, such that what can be in that post body, in our case we're sending over the bytes of the file in that post body, can only be so large. So if we were using, for example, AWS managed API gateway here, it has a limit of 10 megabytes in that post body. So a 50 gigabyte file is obviously far larger than that. We couldn't get through here anyway. We would get an error. So those are the 2 issues. Let me start with the first one because it's the more simple to address, and then we'll talk about how we can handle the bottleneck introduced here. So the first thing, when it comes to making sure that we don't have this redundant upload path and this waste of bandwidth, we can actually upload directly to S3, just like we downloaded directly from S3. But the issue that we run into is, how do we know how to upload directly to S3? We don't want to make it so that everyone can upload to S3. That would be dangerous. And so what we do is when we want to upload a file, we send just the metadata, not the bytes of the file this time, just the metadata to our file service, which writes that metadata to our file metadata DB. It probably updates a field like status to say started or something like this. This is nice to have my schema right next to my database for this reason. You see how we kind of continue to evolve it as we walk through the flows. But we're going to update the metadata. And then instead of uploading the file to blob storage, we're going to actually request a pre-signed URL. And so what pre-signed URLs are they're basically us asking blob storage with our authentication that we had from the file service. We're an authenticated user. We say to blob storage, I want to upload a file of this MIME type, like PDF or whatever else. It's of this size. And then blob storage gives us a secure link. And that secure link basically has some additional metadata at the end of the URL, which is signed by S3, which ensures that the file that can be uploaded is only of that MIME type, only of that size, and it's only available for a limited period of time. You can basically only upload to this link for a short window. Actually, I don't remember what S3's default is there, but let's say 10, 15, 30 minutes or so. So we get that pre-signed URL and we return it back to our client. And then our client can actually then just directly upload directly to S3 with that pre-signed URL. So basically in that REST call to upload the file, we're not going to do it, in that REST call to upload the file, we're not going to do it to our own API endpoint to hit our own servers. We're going to post it directly to that pre-signed URL. So we can upload directly to S3. So fantastic. That solved the first issue. No problem. But we still have the issue of if this is a really large file, then one, this is going to take a huge amount of time, right? So we could do a little bit of math there, and we would find that, to upload a 50 gigabyte file at an average internet speed of 100 megabits per second, this is going to take us 1 hour and 12 minutes. I did that math, just before filming this so that you guys wouldn't have to see us do it in line. But that's good math to do at this time, right? So this would take 1 hour and 12 minutes. That's a long time. And so from a user experience perspective, it would suck if I got halfway through this upload and then I lost my internet connection or something failed or anything else. And I had to all of a sudden completely restart. That would be a bummer. So the way that we handle this is we use something called chunking. Chunking is what's really important here. So what we do is we can chunk files on the client. So chunk files on the client to something like 5 megabyte chunks. These are smaller chunks. And so if we have a 50 gigabyte file here, we'll create all of these 5 megabyte chunks, and we'll update those chunks or upload those chunks directly to S3, one after another, either serially or in parallel, depending on what our bandwidth is. And so we can upload each of these chunks. And importantly, as we're uploading those chunks, we also need to keep track of the status of what chunks have been uploaded. And this is so that, of course, if we fail, we can compare the chunks that have been uploaded to the chunks that we have in the file and only upload the ones that are missing. And so in order to do that, we would need to update our file metadata over here to store those chunks. Now, we didn't talk about what database this was yet. And to be honest, it could be either or any of the common SQL or NoSQL databases. Actually, slight aside, the debate in an interview between whether you use SQL or NoSQL is kind of outdated at this point. These technologies have come a long way. They've converged, and such that when well configured, they can largely do the same things. So I'm going to forgo that argument because I think it's uninteresting. It could be NoSQL, it could be SQL. If it was a SQL database like Postgres or something, then we would use normalization and we would have another chunks table over here that has our chunk information with some foreign key back to the metadata. I'm actually going to opt for going with DynamoDB, NoSQL database, and I'm just going to add it directly on this object then. So I'm going to have a chunks, and it's going to be a list of chunks. And so what chunks are going to have then, each specific chunk item in this list is going to have an ID, it's going to have maybe the status, and it's going to have, its own S3 link, right? So we have a list of all of our chunks. So step one, we took our 50 gigabyte file, we chunked it. We sent that with our metadata, and we said, here are all of my chunks, and maybe all of their status at this point is not started. Then we start uploading each of those chunks, either in serial or in parallel, to S3. As they get uploaded, we can update the status to success, uploaded, and update the S3 link. Now, when we want to resume an upload because it stopped halfway through or any other reason, we simply need to request our file metadata, get our file metadata, and compare the chunks from the file on the client to the chunks in our file metadata, and only upload the ones that are missing. Now, importantly, you might be pointing out that, well, how do we compare the chunks here to the chunks here? We need some unique way of saying that this chunk that I have here is the same as a chunk that you've already uploaded. And so we could do silly things like maintaining indexes. This is not great. It's error prone. And instead, we need a unique way to be able to identify a chunk and to track that chunk's identification. And what we end up using here is something called fingerprinting. So we can fingerprint each chunk. And what fingerprinting is it's just a hash of the bytes of the file, or the bytes of the chunk in this case. So step one, chunk the files. Step two, calculate their fingerprint by running a hash over their bytes. This will give you a unique ID. And then this fingerprint is actually what we're going to store here. Our ID is the fingerprint. And so now when we want to check to see if any files have been uploaded, we're just going to compare the fingerprint of the chunk that we have here stored in our server, in our database, to the fingerprint that we've calculated on the client. And if there are any fingerprints, any chunks on the client that have not successfully been uploaded as determined by our file metadata, then we'll re-upload them. Right. Okay, hopefully that makes sense. Just to recap, what we're going to do here when we want to upload a file is we're first going to store our file metadata and all of the chunk data with their fingerprints as started or not uploaded. We're going to request a pre-signed URL from blob storage. We're then going to upload directly to that pre-signed URL. Now there's one last thing before we move on to another deep dive, actually, that I hand waved and that watchers might have noticed. And that's when I'm uploading chunks to S3, how do I know how to update the status? How do I get that information back to my database here in order to update the status of that chunk? And the reason that this is an issue is because there's a couple ways to do it, but the obvious way is insecure. So the first thing that we would do is we would upload a chunk, we'd get a response from S3 saying that chunk's uploaded, and then we would rely on our client to make an additional request to our server, a patch, put, whatever it would be, in order to update our file metadata to say, complete now. The issue with this approach is that we are directly relying or trusting our client. And our client could lie to us, right? So this could be some malicious user for some reason, and they could tell us incorrect information that a chunk either was or was not uploaded successfully. And then our status would be inconsistent with what actually happened in S3. Now, there's a strong argument here that would say, who cares? Hackers could only mess up their own file upload, so let them do it. But of course, having inconsistency between our metadata and S3 isn't ideal. It's going to cause headaches for the engineering team to debug and etc. So instead of directly trusting the client, we can use a pattern called trust but verify. And so when a chunk is uploaded to S3, we respond saying success, or S3 responds saying success. The client then says, this chunk was just successfully uploaded to the file metadata service. The file metadata service would then check with blob storage. Hey, I just want to confirm. The client told me this chunk was uploaded. Was it? S3 will respond, and then we can update the status in our file metadata. So that pattern is called trust but verify, and that's really useful here. The other option which could be considered is that most blob storage, cloud providers enable some version of change data capture. So basically, you can have some notification that's triggered off of blob storage when something happens. S3 uses something called S3 notifications. So you could have something here that would be S3 notifications. Then anytime a new chunk is uploaded here, then it would notify our file service, hey, a new chunk was uploaded, and then our file service can update our metadata. This way, we're not trusting or relying on the client at all. And so this is fine, this is good, this would work. Maybe it's added complexity, there are pros and cons, trade-offs to weigh. This is the interesting stuff to get into in an interview. It is worth noting that this chunking and uploading is actually really popular. So like S3, for example, just exposes an API called multi-part upload, which does this stuff that we're talking about. It handles the chunking on the client, the uploading, the fingerprinting, the comparing of fingerprinting to validate, etc. And if you were to use S3 multi-part upload, then you would run into a situation where actually on each specific chunk of the multi-part upload, blob storage doesn't support an S3 notification. So nuance there. I don't want to go into more detail, but I know some watchers might call that out. This is an option. If you didn't use multi-part upload, you'd probably want to use multi-part upload, so you wouldn't use this. All in all, the trust but verify approach is the approach that I would probably go for in an interview, but both options are great. Okay, for our next deep dive, let's go ahead and talk about low latency upload and download as low as possible. We've actually done a lot of the hard work here already. This one should be pretty quick. So chunking actually helped a lot here. Beyond you being useful for the resumable upload stuff that we just did, it also helps us speed up this upload process in particular. So while bandwidth is fixed, meaning that the pipe is only so big, chunking helps us make the most of that available bandwidth. So by sending multiple chunks in parallel in particular, we're able to use like adaptive chunk sizes based on the network condition, and we can maximize the amount of bandwidth that we use. Basically use all of the bandwidth that's available to us. So that helped us speed up upload already a bit. And there's a couple other things. We could talk about a CDN, and that's a common thing that candidates like to do, is they like to talk about adding a CDN here. Why does that keep happening? They like to talk about adding a CDN here. And CDNs are great. They definitely bring the content closer to the users, speed up the download process in that way. But maybe top candidates bring up a really nice point when they talk about the CDN here, where they weigh whether or not it's necessary. So in our case, there's a strong argument that it's not. And the justification here would be that users are mostly only downloading their own files. And so by downloading their own files, they're likely located close to the data warehouse or the servers. Like you can imagine that we have this exact thing that you're seeing here replicated all over the world. Right? We have maybe 5 data centers or something. And so the benefit of the CDN is that even if your data is in one data center, one of the benefits of a CDN, but you're out in Germany, you'll be able to download that content from the CDN in Germany, and it'll be super quick. Now we probably don't have that usage pattern here, so it's much less relevant because it would only apply if a user is really traveling, or if a given file is super, super popular. So if we had a ton of sharing and maybe for some reason the Declaration of Independence was in our Dropbox and people all over the world were viewing it or whatever, then the CDN would be great. It certainly would speed things up. You could get closer to the user a bit, even considering what I just said, but it's expensive. CDNs are pretty expensive to manage. So pros and cons here. There's no right or wrong answer. I'm going to opt for maybe not including a CDN just because of that reason, but it's a good conversation to have. Now, another thing that we can do in order to speed up the upload and download process respectively is we can transfer fewer bytes. How can we transfer fewer bytes over the network? Well, we can use something called compression. All right, so compression takes a file, compresses it, runs an algorithm on it. This is like gzip you've ever used on your computer. I'm sure you have. It compresses it into something smaller, into fewer bytes. And by sending fewer bytes over the network, of course, uploads and downloads are going to be quicker. Now, we don't want to just arbitrarily compress things, though. There's a downside to that. We have to decompress them, which makes things slower on the other side. So there are some file types that compress a lot, like text files are known to compress really well, docx files, maybe things like this. But there are other file types, like media types, like JPEGs, PNGs, .movs, MP4s, etc. These are already naturally pretty well compressed. So running a compression algorithm on them is only going to gain you a couple percent decrease in the size of the file, which isn't worth it, considering that we have the added time that's going to come from the compression and the decompression. So you can end up doing some kind of intelligent compression logic here on the client again, based on the file type, based on the network conditions. Should I compress or should I not compress? And then maybe we add to our file metadata then compression algo. If we did compress, we would need to specify what that compression algorithm was so that we could decompress respectively. Okay. I think that's just about all there is to speeding up uploads and downloads. Relatively straightforward there. The chunking helped a lot. Of course, the CDN is a good conversation to have. And then potentially using compression algorithms, but they don't make sense in every case, certainly not for every file type. Okay, let's go into our last deep dive now, and that's going to be this high data integrity for sync accuracy. Maybe more generally, let's just talk about all the ways that we can improve this sync between our local folder, our local file system, and our remote repository or remote file system. So when it comes to syncing, there's two things that are important to us. We talked about the remote change, we talked about the local change. Now let's talk about two potential optimizations. So deep dive on sync. The two things that we care about is the first one is how can we make sync fast? So we want this thing to be as fast as possible. This is within reason, of course, but what this means is that when something changes on remote, we want it to be reflected on our local folder kind of as soon as possible. Again, within reason. So that's the first one. And then the second one is that we want sync to be consistent. And so what this means is that whatever is in our local folder should be what's in remote. Whatever's in remote should be what's in our local folder. So we're going to talk about these two things and some optimizations that we can do for both respectively. Let's start with talking about how we make sync fast. And so the first thing is, how can we know when there's changes? We had talked about periodically polling for changes. And to be honest, I think this is still the best approach. So this means that the client here can just poll the database to know when something has changed. And we can play with the frequency and the intervals. So if they have their client app open, if there's been a lot of changes recently, if they're playing around in that folder, maybe we decrease the delta between our polls. So increase the frequency of our polls, how often we're checking to see if there were changes. That can be kind of like adaptive polling. The other option that candidates oftentimes bring up is either WebSockets or sometimes even long polling. These are options, but they're totally overkill. Right? You're not going to want to set up a persistent, always-on connection between your client and your remote server here when it's kind of always open, right? Literally always open, because it would be open anytime you're using your computer. And it introduces a bunch of additional overhead. You need a WebSocket manager. You need to be able to maintain that. It's overkill for this system. And from a product requirement perspective, do you care if you see the updates within seconds or within milliseconds? Or is it okay if you see them within 10s, 20s, seconds, a minute, whatever? And of course, on the client app, we can always put a refresh button. So if you really need that file there, you can click that refresh button and it'll kick off a poll if that poll hadn't happened yet. So in my opinion, that's overkill. Long polling doesn't make as much sense either. Long polling is when you're going to make a request and then you're going to keep that request open for about a minute or so for the server to be able to respond. This is when you're expecting a response or several responses, but still within a relatively quick window there, that minute or so window. And that's not the pattern that we have here. We don't know when changes are going to be made and are going to need to notify us. So polling with some adaptive frequencies here, I think is fully appropriate. But then the next thing is if a change gets made to a file, let's say some change got made to a file in our remote server here, then we don't want to have to download that entire file and update it in our local folder, especially if that was a big file, that 50 gigabyte file. So this is where chunking comes in again, right? So now what we're going to do is something that I think Dropbox refers to as delta sync. And so what this means is that we're only going to get the chunks that have changed. So we probably want to add, like an updated at here too. And what we do is when we pull for changes, we'll just specifically look for the chunks that have changed in any given file. So maybe there's a new file that was added, in which case we have no choice. We'll download the entire file, of course, we'll update our local DB, and we'll stick that file in our local folder. But in the case where we just made some changes to a single file, which is fairly common, then all we need to do is download the chunks that have been updated since kind of our last sync, our last pull. And so we can just download those chunks. Our client app will do the stitching for us to make sure that our local file in our local folder here now has that updated chunk. And this will help with speed a bunch because it'll make sure that we're only downloading that latest chunk. So I'm going to say here that we're going to do some adaptive polling, and then we're also going to do delta sync to only fetch changed chunks. So those are kind of the two things that we can do there. Okay, when we talk about consistency, this is where it introduces maybe some more interesting questions. So I keep referring to polling, but I'm intentionally been a little vague up until this point as to what that actually means. And so let's talk about what our options are there. The first and the most obvious is that we can poll the database directly. We can just say that for any, we'll probably need some reference to a folder or user. So actually that's probably good to have here. This is folder ID. This is the folder that's synced, right? So I can say for folder ID 123, get me any files for which a chunk has changed or been added since our last sync. This would be pulling the database directly. All right? Pretty easy, pretty straightforward, great option. Option 2, and this is closer to what Dropbox actually does for what it's worth, is that we can have an event bus with a cursor. And so this is a fairly common pattern, and I'll sketch it out without maybe putting all the gritty details in here. But this is going to be an event stream or an event bus. So this could be something like Kafka, right? Kafka is always a fine choice here. And so what's going to happen is that any change that occurs to any of these given files, we're going to put that change event on this bus. And then we'll need to have some kind of additional data structure, which we probably should have had, or some additional state here, which we maybe should have had anyway. But we're going to have some folder, and that folder is going to have a cursor, and this is the sync cursor. Let me call it the sync cursor. And so as events or changes are coming in, we're going to put those changes on our event bus. And so now the very first time you set up a local folder, then you're not going to have any cursor here. So we're going to replay all of these events in order to construct the correct local state. Basically, here are all the things that have changed in the lifetime of this folder. Go construct that in your local folder, in your local DB, create these files. All good, right? We'll request that from the sync service. And then we'll update the cursor to say, this is where you were in that update process. The last event that you read was this particular cursor. And so the next time that we want to sync, when we do our next periodic polling, instead of going to the database and asking for changes, we're going to come down here to our event bus, which is a linear list of the events. Kind of think of it like a linked list. And we're going to navigate to the cursor, basically the last event that we read, and we're going to take all of the new events that have come in. We're going to apply those changes to our local DB. So this is definitely more complicated. You would talk about some additional things here, like partitioning on either user ID or folder ID. This thing's going to grow. At some point, you want to consolidate changes here. So like you don't want to have to read every single event. Maybe you have a snapshot point where you can just restore from something directly in file metadata and then read events from there. The reason that I'm being a little bit intentionally vague here and not going into too much detail is because while this is what Dropbox does, for this design, and given our functional requirements and our non-functional requirements, I think this is overkill. And the reason being that an event bus with cursor is great for when you need an audit trail and you need some version control. It allows you to do data recovery. You can roll back past events to go to a previous point, right? Roll forward. And so it's great for all of those reasons. We didn't have that in our functional requirements. So we didn't explicitly say that we want to have an audit trail, that we want to have version control. And for that reason, I call this overkill. Now, in your design of Dropbox in an interview, maybe that is something that's important. So I wanted to bring this up because it might be necessary, but it adds a ton of complexity that's kind of not necessary relative to just pulling the database and looking for changes. Now, of course, if we made a change to this database, we would have overwritten a chunk. And then we don't know the old chunk. So we can't handle versioning, we can't roll back, whereas with the event bus, we could do something like that. So that's the change there. I'm going to delete it, because it's not making it into my design. I'm going to opt for simplicity here. But that's the way that we could handle that. So for sync to be consistent, it's either pulling the DB or it's an event bus with cursor. And there's probably other options there, of course, too, but those are the two main ones that I see pop up in interviews most often. And then the very last thing that's worth discussing is that despite all of our best efforts, it's possible that our local folder and our remote fall into an inconsistent state. It can happen. There's a lot of moving pieces here. Anything could break at any point, whether it's a developer bug or issues that we had with connections, etc. So what's oftentimes applied in these situations is something that's called I'm not going to be able to spell this. Reconciliation. Anyway, kind of adding reconciliation here. And so what this is that periodically, maybe it's daily, maybe it's weekly, whatever it needs to be, your client app is going to go fetch all of the information in remote for this folder. And it's going to compare it to its local DB and compare the fingerprints to the files that it has in that local folder and make sure that everything is totally consistent. And if there are any issues, then it's going to handle reconciliation. It's going to fix those issues. And so while our more real-time, quote-unquote, real-time syncing of these two should get the job done, in case there are any issues, no problem. We'll periodically do reconciliation, whether it's every day or every week. Quickly, before we recap, I just want to call one thing out that I mentioned and failed to come back to. When we did these APIs, I told you these APIs were wrong. You'll see now why that API was wrong, right? We don't post the file with the file body or with the file itself in the file metadata because we ended up writing directly to S3. So let me grab, kind of what's a more correct one here, and I'll update it. This is a good thing to do in the interview, but not necessarily. You want to talk through it. So this is now where we have those. First, we post with the file metadata and we get back a pre-signed URL. Then we upload the file chunks to the pre-signed URL. And then we update our file metadata with the chunk status as we're going. So I just updated those so that when you guys have this resource, you have something that's accurate. Okay, fantastic. So we went through all 5 of these steps. We did our requirements, core entities, API, high-level design, and deep dives. I think we ended up landing on a pretty good system here that balances simplicity with meeting all of our requirements. So I'm going to continue to try to I've been doing one of these every 3 weeks. That's the pace that I'm going to try to keep up. I'm going to put a link in the description with a couple of things. Of course, there's going to be the link to the written version of this. There's also going to be a link to a place on the website where you can vote for the question that you want me to do next. So head over there, vote. If you're enjoying these and you want to see a different question, you can suggest a question or vote on a question directly. And then I've really been enjoying your guys' comments. So there have been some really encouraging comments that are motivating me to continue to keep doing these. I really appreciate reading those. There have also been some people who have pointed out, whether it's great questions or things that were inaccurate. Please do that here. I'm largely doing these in like one-ish take. It takes a couple takes, but I just run through it and talk about the things that I believe to be true and have experience from doing these interviews, but these aren't particularly well rehearsed, so I'm sure there's times where I misspoke, there's inaccuracies. Call those out in the comments. Let's talk about them. I want to hear from you guys and answer as many questions as I can. So, as always, thanks again for watching. We'll have another one in 3 weeks or so, and best of luck with the upcoming interviews.